All right, guys, we're going over the practice exam questions. This is pretty much as long as your practice exam will be. On Thursday, we will do a timed practice exam to see how that goes. All right, so first we have our paragraph length response. Block goes up the ramp some distance. And the first thing that we need to do is think about the free body diagram as this goes up the ramp and down the ramp. Of course, in both cases, you're going to have gravity acting down, and you're going to have the normal force making sure it's perpendicular to the surface, and that's not going to change whether or not it goes up or down the ramp. That's going to be the same. If you really wanted to be accurate, you'd also show the normal force is less in magnitude than the force of gravity. On the other hand, while you're going up, you have a force of friction, which is going to be smaller than the normal force going down the ramp. But then as it goes down the ramp, you will have the same force of friction, but it will be going up. So that's an important thing to keep in mind. And what we always try and do here as well, every time we do this, we're thinking about gravity and breaking it into those components, right? And so what we can see here is that when we're on our way up the ramp, friction and gravity are acting together. So that net force is going to be the sum of the parallel component of gravity and the force of friction. While on the way down, there's a difference since these are in opposite directions. Um, so, since the acceleration is dependent on the net force, that means that when we are on our way up, we have a greater net force and a greater acceleration than when we are on our way down. That means that the time up should actually be less than the time down. Um, when we think about up and down having the same value, that's only going to be true if it's the same magnitude of acceleration both ways, or the same acceleration both ways. In this case, it's different. And so that's what your reasoning should explain. It should be connecting the, you start with, well, what are we asking about? We're asking about time, and then we work from there and we say, well, what does time depend on? It's the same position in both cases. So this distance is the same, so that's something that will be the same. But it's dependent on acceleration and initial, conditions. If you went as far as to show the equation, we could say, well, we're probably using the, x is equal to x initial. Whoop, I just screwed that up. X is equal to x initial plus VIT plus 1/2 AT squared. So that's going to be how we're going to solve that. So you could have done it a few different ways, but mostly pinpointing on the fact that the accelerations will be different in those two different directions. One other thing we could point out is that, yes, I start with initial velocity at the top and a final velocity, but since work is being done against the motion, since energy is being lost, we can also say that the final velocity when it gets back down to the bottom will be less than the initial velocity when it left, if you wanted to approach it from a conservation of energy standpoint. So there's a lot of different ways that you can do it. You can get some points even if you answered this part wrong by including some faulty but coherent and consistent reasoning. But the main way that we want to do this is to base off of a free body diagram and simply know that we're going to have different accelerations. All right, so for the second question, this should be something that we're fairly familiar with, right? We got like these connected systems, and then we understand that the net force on the total system is divided by the mass of the total system. That means that we should think about this in terms of the acceleration is equal to, and if we did divide it out properly, we should see, m b times g, right? That's the force that's acting on this, divided by ma plus mb, and that ma is not mass times acceleration, that's just the mass of block A. I don't have the way to do subscripts in this system. All right, so we should understand that, and then we should look at things on a part and a whole. So the question is, if A is much greater. Now, if we're talking about much greater, you are talking about orders of magnitude greater. So we shouldn't be thinking like 10 more. We should be thinking like 10 or 100 or 1,000 times more. All right, so let's think about this. If A is 1,000 kilograms and B is 1 kilogram, what does that mean for this system? Now, it is frictionless, okay? But as you get much greater, what you end up seeing is, well, the force of block B on A is going to start to approach being negligible. Which means, if A is 1,000,000 kilograms and B is 1 gram, and that's the kind of comparison you can do for these much greater scenarios, essentially the acceleration would be 0, because you have acceleration is force divided by mass, but if the mass is so humongous in relation to that force, it's approaching 0 at the very least. Similarly, if we say A is much less than the mass of B, so imagine you have a 10 kilogram mass that's attached over this pulley to a paper clip, we can kind of see that the force of A on B is going to be negligible, and B is going to just drop to the ground with roughly the acceleration due to gravity. And that is really what we should be looking at for those, is to say, well, if A is much greater, the acceleration would be essentially 0. If B is much greater, then the acceleration will just be that of gravity, because B is just going to fall to the ground like normal. And so when it comes to the diagrams, of course, B just has the force of gravity down and tension up, while A is going to have that force of tension this way, the normal force on A, and the force of gravity on A, and there is no frictional force. So I would hope, and I think what I did see, you guys had that part pretty well down. On the other hand, and I just showed you the equation, right? The acceleration is it'd be mbg divided by ma plus mb. And that's just by combining those free body diagrams. And if we do look at what happens in these equations when we are actually solving for this, so remember, A is equal to mb times g divided by ma plus mb. We can kind of look at this and just say, what's going to happen? Well, if ma is super large and mb is super small, g is just a constant. So when ma gets really, really large, you're just getting closer and closer to 0. On the other hand, right, so I kind of get to neglect MB and just focus on MA. On the other hand, if MB is very large, then I get to ignore MA, and I get MB times G over MB. That's going to cancel those two masses out and just leave me with G. And so that's basically the solution that we should be looking for. Hopefully you guys were in the ballpark, and I will see you guys soon.